Hello and good morning, everyone. My name is Ghaziabad, and I am Assistant Professor in Department of Computer Science in ABES Engineering College. My today's topic is BFS or breadth first search in data structure. Now, what is BFS? Let me go to my next slide. This lecture contains different contents like what is BFS, pseudocode of breadth first search algorithm, the explanation with an example of this pseudocode, the complexity of breadth first search, and also the application of BFS. BFS or breadth first search. Well, now what is BFS? Breadth first search or BFS is graph traversal algorithm. Graph traversal algorithm. Graph, what is graph? Graph is a non-linear data structure consisting of vertices and edges like this. These are vertices, they're connected through edges. Sometimes these vertices are also called nodes and edges, arcs or lines. Okay, so a graph is a collection of vertices and edges. It's a non-linear data structure. Now, what is traversing? Traversing is a basic operation in data structure. Means you have to access each node at least once in a data structure is called traversing. Like this, traversing is a basic operation in data structure. It is a process to access each element in data structure. Means accessing each node at least once. So in any data structure, just like here, there's a graph. If you are accessing each node at least once or each vertices at least once, that comes into traversing. So if you're talking about graph traversal algorithm, there are two algorithms out there, breadth first search and depth first search. The first one is BFS or breadth first search. Now, what is breadth first search? I have already told you. What is the pseudocode of breadth first search? This is the easiest pseudocode for BFS algorithm. What it says, initialize all the nodes to ready states. That means whatever vertices are given, initialize them to the ready state. Here in the pseudocode, you can see that there are three states: ready state, second one is waiting state, and third one is process state. The processing is same as accessing. Okay. So first of all, initialize all the nodes to some state that is called ready state. Now we are using here a data structure called queue. Okay, in DFS we used to use stack, but here we are using queue. So put the starting node in queue and change its status to waiting state, the second state. And now in BFS, most of the time, whenever we are putting some nodes or vertices in a queue, it will come from ready state to waiting state. Keep this in mind. Whenever a point, not no point, a node or a vertex is in a queue, that will be in a waiting state. Now, what is the third step? Repeat step 3 and 4 until queue becomes empty. I will explain you this pseudocode with an example. Just go through this. Okay, so the fourth step is saying the fourth and fifth we have to repeat again and again until the queue becomes empty. The fourth step is saying remove front element of the queue. As you know, in queue data structure, the deletion or removal of an element is from front. Okay, that's why it is saying remove front element from the queue, process it, and change its status to process state. This is my third state. Just like the first one was the ready state, the second one was the waiting state, and after processing, we are getting the third state that is called process state. Now, add to just after the fourth step, we'll get to fifth step. And the fifth step is saying add to the rear of the queue, add to the rear of the queue all the neighbors nodes that are in ready state and change their status to waiting. Now, here are two important points are there. Only those neighbor nodes will be in the queue that are in a ready state, not the process state one. And the second one, whenever you are putting any node in the queue, that will come to the waiting state. Now, if I will implement, I will take some example and implement these pseudocode. You will learn, you will understand what I want to say. Suppose this is a graph. This is an example. This is a graph containing A, B, C, D, E, F, G, H. These are the vertices connected to edges. Okay, I have to apply this algorithm in this given example. So the first point is saying initialize all the nodes to the ready states. Nodes are A, B, C, D. So my first step is this. I have initialized all the nodes to the ready state. This is the symbol of ready state. This is the symbol for ready state. So I have initialized all the nodes. You can see on this example, I have initialized all the nodes. And there is a queue that is using that I will use for traversing this particular graph. And this is the starting point of the graph, the point B. It is given initially. So this is the graph, and this was the graph, and I am applying my BFS codes on this. Okay, so the first step is initialize all the nodes. So I have initialized all the nodes like this. This is the ready state. This is the symbol of ready state. Now, what second point is saying? Put the starting node in the queue and change its status to waiting state. Put the starting node in the queue. So my next step, second step is starting node was B, right? Starting node was B. So this is my starting node. I have put it that node in the queue. So this node will be front as well as rear. There's only one node is there in the queue. That's why that is front as well as rear. And this is the symbol. Look, this is the symbol for waiting state. So whenever I put any node, as I have told you earlier, whenever I will put any node in the queue, that will come to the waiting state from the ready state. Initially, this node was in ready state. Now I have put it that node into the queue as per the requirement of our algorithm. So here comes waiting state. The other nodes are in the same state, but that particular node will be in ready state. Now, again, I will go to my algorithm, initialize all the nodes. We have done that. Put the starting node in the queue and start it and change its status to waiting state. I have already done. Now, go to the step 3. Okay. Repeat step 4 and 5 until queue becomes empty. Now, my queue is not empty here. Okay. There is one element, that is B. There is one element already there, that is B. So I will apply my algorithm like repeat step 4 and 5 until queue becomes empty. In the fourth step is saying remove front element of the queue, remove front element of the queue, process it and change its status to process state. Look, as we all know, from the queue, the removal is done from the front end. So that's why it is saying remove front element of the queue and process it and change its status to process state. So I'm removing this element. This is the front element B. Okay, I'm removing this. So I have removed that element and I have changed its status to process state. Now this is the symbol of processed state here. This is the symbol of process state. So there were 3 states. This is the ready state, this is the waiting state, and this is the process state. So as I am following the algorithm. So algorithm is saying repeat step 4 and 5 until queue becomes empty. And the fourth step is saying remove the front element from the queue and process it and change its status to process it. I have done that. Now what fifth step is saying? Add to the rear of the queue. Add to the rear of the queue all the neighbor nodes that are in ready state. This is an important thing. All those neighbor state or all those neighbor nodes that are in ready state and change its status to waiting state. As we all know that the nodes that are in queue state, sorry, that are in queue will be in waiting state. So I have processed this, and after processing, according to the fifth step, all the neighbors of this state, that is A and B, only there are two nodes, node A as well as node G. These two are the neighbor nodes of B, not H, not C, because they are not directly connected. Okay, they are not adjacent to B. That's why they are the neighbor nodes. Okay, so A and B will A and G, not B. A. B is the processed state. Now node B is now in process state. Now A as well as G will be in the queue, and after getting into the queue, their status will be waiting state. Okay. Now again, our queue is not empty. Our queue is not empty. As algorithm is saying, repeat step 4 and 5 until queue becomes empty. So we have to follow these both these steps. Step 4, that is saying remove front element, and step 5, that is saying add to the rear of the queue the neighbor nodes to the queue. Okay, so we have to follow these 4 and 5 step again and again and again until and unless queue becomes empty. So just go through this point. After doing this, G is the front element. G is the front element. So I will remove this element, process it, and after removing this element and processing this, we will convert this element in the process state. As I am highlighting this into the process state. And after that, this was the fourth step. As I have told you earlier, the fifth step was that all the neighbors, like G has three neighbors, B, C, as well as F. Now B is in process state. So only C and F is in ready state. So we will convert that into waiting state and it will go to the queue. Now you can see there are three elements in the queue: A, C, and F. A is in waiting state, C is in also in waiting state, and F is also in a waiting state. But B as well as G are in process state. Means we are already done with this, these two vertices, or you can say nodes. Now again, step 4 and 5. Step 4 is saying remove the front element. Now in the front, after removal of G, A will come to the front and A is in the front node, front position. Now remove A is here. Remove A, process it, and change its status to process state. And all its neighbor, like H and B, that are in ready state. So here H is only in ready state. So we'll change its status only to waiting state. Now see, A is processed, A is in process state, and its neighbor H is in ready state. And just because of that, we have added this H from the rear of the queue. Because the addition in the queue is from the rear and deletion or processing is from front. Okay. So again, step 4 is saying process C. C is here. And after processing C, we can see that F is already in a waiting state, but D is not in ready state. So according to the algorithm that was saying that all those nodes that are on ready state, change their status to waiting state and put them into the queue. So after H, there's one also node is there in the queue, that is D. So accordingly, after B, G, A, C will be processed and it got changed to process state from waiting state. Now accordingly, we will do F, H, and D like this. After removing F, we'll change its status to process state. And its neighbor E is in waiting state because now this is in the queue. Accordingly, after H, there is D. Where is D? D is here. Okay. After H, this is H. This is H. Okay. After removing H, we'll see its neighbor. H neighbor is A, and A is in which state? It is in a process state. So we'll not put that in the queue because our algorithm was saying that add to the rear of the queue all the neighbors nodes that are in ready state. Only those nodes that are in ready state, put them only put them, not other nodes that are in waiting state or in process state. We don't have to put them. So here it is. After node E, after after node H means this one will do processing of this end. That means D. D is here. And after D, because after processing D, we'll see that E, its neighbor, E and its neighbor C already are not in ready state. They all are in either in process state or in waiting state. So we'll not change their status. And accordingly, we'll do processing of D and E. And now you can see that at the end point when the queue is empty, all nodes A, B, C, D, accordingly, they are processed because their status is processed. And that was the thing I was saying to you, traversing of a graph, accessing or processing each node at least once. And at the end, after applying breadth first search, you can see that all the nodes are processed. Now, again, I will repeat that algorithm. We have initialized all the nodes to the ready state like this, initialized all the nodes to the ready state. Okay, put the starting node in the queue and change its status to waiting state. What we have done, this was the starting node. Okay, so we have put that node into the queue, and this node is front as well as rear. And whenever we'll put any node into the queue, we'll put its status to waiting state. That's why it is in a waiting state. And all other nodes are unaffected with due to that. And after that, there are two steps, 4 and 5, kept on repeating until and unless queue becomes empty. In fourth step, we'll do processing. In fourth step, we'll do processing of that particular node that is in front. And in fifth step, we'll put their neighbor, their adjacent neighbor that are in ready state into the queue and will change its status to waiting state. Now, after processing this, we can see that these two nodes that are the neighbor of B are in waiting state. Accordingly, this node, these two are in waiting state. Accordingly, this node is in waiting state. And accordingly to this node has changed to waiting state after processing this element, because our algorithm is saying 4 and 5, this is doing processing, and fifth step is doing what it is doing, all the neighbors that are in ready state change their status to waiting state. So this is the algorithm for breadth first search. It is using queue data structure for accessing each node for traversing. Now we'll go over next slide. Here, this was the last step where I have done all the nodes, and now the queue is empty. So we'll not repeat 4 and 5 again and again. We are done with our pseudocode. Now, what is the complexity of breadth first search? As we can see on our screen, insertion and deletion operation in the queue. That is from insertion is from rear, or deletion is from front. Okay, that will take big O of 1. So accordingly, BFS will, the time complexity of BFS is order of V plus E. V stands for vertices, E stands for edges. Okay, so V plus E. And what are the applications of a breadth first search? Well, for unweighted graph, we can find shortest path, or you can say minimum spanning tree. For finding shortest path and minimum spanning tree in unweighted graph, we can use breadth first search or BFS. In the similar manner, in a graph, if we want to check the cycle for the cycle detection, because the tree, it has no cycle. Okay, so here we are using minimum spanning tree and with the help of breadth first search. So for the cycle detection, we use BFS. Okay, if there is a cycle, there will be no spanning tree. Okay, so with the help of BFS, we can check that. And the last one is to find the length of a path. Suppose we have given some two nodes, some initial node and some goal node. That is in AI most of the time. In AI, we use BFS, breadth first search. Okay, so to find the length in between those two, in the initial node and in some goal node, we have to find some path. We have to find the length of that path. We use breadth first search. So This is what all about breadth first search. This is the first traversing algorithm in graph theory in data structure. I've taken these algorithm from the libs. Well, it's from Shom series. This is my reference. Thank you. Thank you all of you.